Hello, thanks for the invitation, Jordan. So this is Bocho. I am a organic chemist at University of California, San Diego, and today I'm going to talk about the chemical structure and synthesis of ionone. Okay, let's get started. So the term ionone is derived from Iona, which means violet in Greek and none for ketone. So it has three constitutional isomers, as Bruno has mentioned. And here is the structure of the ionone. You have alpha, gamma, and beta ionone with one double bond at a different position. And the beta ionone have the double bond in conjugation with the alpha beta unsaturated ketone right here. And it is a 13 carbon terpenoid or isoprenoid. I'm not sure if this structure, the vinyl, looks familiar to you. If yes, then it is actually related to the one of the structure that we talk about in class in Chem 151, which is a really good class, by the way. Strongly recommended. Haven't taken it. So the structure that I know is related to is beta carotene. As we know, as we talk about in lecture, beta carotene is a pigment and also a nutrient in our in our bodies, and beta ionine can actually be synthesized biologically from beta carotene through an enzyme called BCO2 or beta carotene oxygenase. So it works kind of similar to the biological pathway for getting vitamin A. So to get vitamin A from beta carotene, it is from another enzyme called BCO1. So from BCO1, you'll get retinol right here. And from retinol, it will get reduced into retinol, which is vitamin A. But from another biological pathway, you will get the beta carotene will be cleaved 2 times to get 2 moles of beta ion from 1 mole of beta carotene, and also with a side product of rosafluin, which is a compound commonly found in roses. So, as we said, this is the biosynthesis, and we call that nature is the best organic chemist, although it is not really good at one thing, which is the yield. So, if you want to make a perfume out of ionone, you have to extract it from flowers, as Jordan also mentioned. But if you want to get 1 kilogram of ionone, you actually need to extract 33,000 kilograms of violet. And this is problematic because, first of all, it is time consuming. Second, it is expensive. And most importantly, it is a huge waste of beautiful flowers. And we don't really want that. So this is when organic chemists come into place. So in 1893, 2 chemists called Telemans and Cougars, they come up with these beautiful reactions. Only 2 steps, but simple and easy to run. So you can start with the reactants citro and acetone, and you go through 2 steps, and you will get all three uh, isomers of iron, so alpha, beta, and gamma, by controlling the catalyst of the second step. So if you use a strong acid such as sulfuric acid, you will get beta ionone. If you use a weaker acid like phosphoric acid, you will get alpha ionone. And if you use a Lewis acid like the BF3, you will get gamma ion. And this reaction is really beautiful because the starting material is really easy to get. So acetone, you know, it's a common solvent. Citro, it is just an aldehyde with saturation, and you can easily be obtained from isobutane and formaldehyde. And the mechanism is even more beautiful, which involves an auto condensation, the first step, and a cyclization or ring closing mechanism of the second step. So the first step, you will have the acetone first deprotonated by the base catalyst. Yeah. So the acetone will act as a nucleophile, and you will attack the citro carbonyls group to generate the aldo compound. So you will have the aldo, so the aldehyde or ketone and the alcohol here. And then you will have the condensation or the dehydration step to generate water. And then the hydroxide group here will leave to regenerate the base catalyst. And then for the second step, you will have acid, which depends on which isomer you want to get. So a strong acid for beta ionone and a weaker acid for alpha. So the acid will generate a cation, and the cation will go through rearrangement to create a 6-membered ring right here. And then the last step is the deprotonation of a hydrogen from the atom from the carbon, and that carbon and that deprotonation will lead to our final product. So our beta ion here is due to the deprotonation of carbon right here, the a tertiary carbon. And it is the more thermodynamically stable product, because if the double bond, as I mentioned earlier, is in conjugation with the unsaturated ketone. While the alpha ionone, on the other hand, is the kinetic product, because it is produced from the deprotonation of the last sterically hindered carbon, which is over here. So you can control the residual selectivity of which compound you want to get by using different types of acid catalysts. So that is why this reaction is so beautiful. However, it has one thing, that it is not really favorable to generate the gamma ionone, which is the last stable isomer, because to generate the gamma ionone, you actually need to deprotonate a primary carbon, which is not really acidic and is not really favorable. So there are other methods being studied that are used to generate the gamma ionone, which is actually have stronger than better scent than the alpha than beta isomer. But anyway, I think that's what I have so far. And thank you again, Jordan, and Bocho out.